So in this practical, I'll show how to estimate heritability using maximum likelihood approach that is based on concept of probability density function and likelihood that was shown in the second lecture. So similar in the first practical, so you need R and library mass, and all the course material can be downloaded from the web. The address is here. So I guess you have already all the material necessary for this practical. So that is you need some R code, and probably you need some R in your machine at the moment. Okay, so probability density function from the lecture, it looks like this. It's function of the sigma standard deviation, or sigma square is variance, and mu is mean of the population, and this x is a variable, for example phenotypic value. Can you draw normal curve and what is probability density function? I will show using whiteboard. Yeah, so this is normal curve, and if this is standardized, then mean should be 0 and standard deviation equal 1. So that is this one as shown in the first lecture. The density that is given value here or here or anywhere here, then when the height at the curve, so this goes to here, then this y-axis is actually probability density value, right? So if the value is given here, then probability density should be this value. Is that make clear? Then can you write the R code for the function above? So probably you can follow this equation. So I already put in the R code. I can show here. If you open pdf.r, then given mean is 0 and standard deviation 1 is standard normal curve, then actually this equation is written as here, this one. This is the same as this one, right? Then can you find probability density function in R? So R code, R command is denom, there is probability density function. So when you run this R code, then you can compare PDF1 and PDF2. Is it okay? So we can close this one and next question. Yeah, so this is I already show. You can check it out, the pdf.r code, and compare. Probably you can write code by yourself and compare to this pdf.r and try to run. Maybe we can try run open source pdf.r. Yeah, then we can. So if we add the pdf1 is 0.086 and pdf2, yeah, it does get the same value, right? So you can see this command and this command is the same. So this is the probability density given the variable value as 1.75. So maybe I can, this is to show, sorry, this one. So that is around 1.75, so probably around here. Then when you go to this value, then this should be 0.08. Does that make sense? What is the norm in R? That I just show there is probability density. Then what is phenom? That is cumulative probability density. Then what is QNOM in R? So QNOM is first we try denom. So this is given the y value or penalty value 1.75 in the standard curve. There is a mean 0 and standard deviation is 1. Then you can see probability density is 0.086. Then when you do phenom, there is accumulated probability density. Then that's around 96%. So maybe I can show again with whiteboard here. So given if this is 1.75 value as a penalty value, then probability density for this point at this curve is around for example 0.08, right? So that is the probability density function. This is PDF from this one. This is PDF. Then cumulated probability density function is integrating this all part. So this is around 96%. That is you can get using phenom, right? Then what is a QNOM? QNOM is actually inverse of cumulative probability density. So from the phenom, you know that at point 1.75 you get around 96%. Then in other words, if you use QNOM and now give input as point same as 994. So this tell what if the path is around 96% at the standard normal curve, then what is the point that give this value. So this is a, then you can see this value and this value is same, right? So this is a inverse cumulative probability density. Did that make sense? Can you explain probability density function, and can you explain likelihood? What is difference between PDF and likelihood? So if we see the previous lecture, so as I explained in the lecture as well as just the last slide, probability density function as command as in R, that is given the y value, then what is height at the curve, right? So this is a probability density function. That you know the probability density function. Then what is likelihood? So if we go, yeah, then given phenotypic value for the population, then you can give some value for the mean and sigma, the variance or standard deviation. Then for the population, you can work out probability density function for each individual. Then the product of all this probability density, you can get this value. So this is likelihood. So given the matrix notation, so you have this probability density function, right? Then what is likelihood is given the y value. Then if you give mu and sigma as input, then you get the product of probability density. That is likelihood. Did that make sense? Maybe I can explain again here. So the probability density is given the mu and sigma, then the input of phenotypic value, then you can get probability density. Then likelihood is for the population. So that now then phenotypic value is given for the population, right? Then you can give input of mean and sigma. Then you get the product of all this probability density, then this value is likelihood. So I will now introduce how to use grid search to estimate sigma or standard deviation given observation. So now we will obtain maximum likelihood of estimate for variance x or variance y. So you can see pdf-grid.r in R code. So can you work out how PDF be used in the grid search? So this is the code that is shown in the pdf-grid.r. So I set the number of record is a lot, 100,000. Then initial the value for the mean I give 2.7 and standard deviation 3.6. Then I get the normal distribution function from the R, then I get the 100,000 value for the YV. So this is a kind of simulations, stochastic simulation given the true value. Then now we estimate the mu and standard deviation using sum of log probability density. So you can see how to use this probability density, right? So first you can guess standard deviation. This is as input. Then from the 1 to n record, then this is a product of a PDF. So you can use the function denom, that is get the PDF, and given mu is fixed, then you can give this standard deviation value from guess, then you can get the likelihood. Then you take logarithm, so you can get log likelihood. Okay, so maybe you can try with this code source and PDF right. So so this is a given value, then you will get the likelihood of minus this value 270 something. It's a lot better, but given only this test, you don't know this is maximum likely estimation or not. So you should check it out the number of different points, right? Let's try grid search for maximum likely estimation of the sigma. So following the instruction, run it and turn off the simulation part so that your y variable is already the same. So let's try. So we tried this one. So now we fixed the part for the simulation. So we go start with this one, right? Yeah. Then save the code. Then we guess standard 2. So we give now changing as 2. Then try. When you try 2, then we get minus 323,000, right? So I will record this in probably in Excel file, then I will float later and show. So now I'm recording, so in Excel, slow. Anyway, now we'll try point 2.2, then try again. Okay, now I got minus 304 something, so let's call it here. So my machine is at the moment very slow, so I got that. I'll record it here. Yeah, then yeah, although this is skipped, but also you can try 2.4, 2.6, 2.8 something until 4.8 and 5, right? Then you can get the nice curve. Okay, so can you make a plot of likely value for this value? Yeah, let's try again. Now I change it to 0.4. Then try again. Then you get this one. So I have made each point for the all value from 2 to 5 interval as 0.02. Then what is estimate standard deviation from the discrete search? So I'll show what I made. Yeah, so this is from 2 to 5 with interval as 0.02. Then this is log likelihood for each point. So this is from each point, then get the likelihood curve. So as you can see, the maximum likelihood estimation is around 3.6 or 3.7, right? From this is grid search. So when you compare the true value, that true value is here. There's 3.6. So it is pretty close, right? So if you want, probably you can make a more finer interval rather than 0.2. You can use 0.1 or 0.05 is more final interval than to get the more precise the estimation what is the maximum likelihood. But basically this shows using grid search actually you can estimate the maximum likelihood value for the sigma. Okay, so now this exercise you can do by yourself. Try with the different mean number or sigma number through sigma through mu, and also number of different record. Then to see what happened and to check still you can still find the maximum likelihood estimations. Probably this number of records should be affected at terms of power. Okay. So far we have done for the grid search to estimate the sigma. Now we can try with the Newton-Raphson method. So looking at the code, then can you work out how probability density function is used in the Newton-Raphson algorithm? So we open the PDF Newton-Raphson.R code. So here, yeah, the simulation part is the same. Then estimate UNST using sum of log PDF. Yeah, that is grid search, and now this is Newton-Raphson. So always Newton-Raphson method need the starting value. Then this is kind of iterative approach. Then from the some calculations, so this is first derivative part, and this is the second derivative part. Then function of first derivative and second derivative, you can get the updated value, then you can get the estimation. So this first derivative, second derivative is shown in the lecture that I can show here. So lecture 2, right? So this is the first derivatives that is written in here from some calculations, and this is second derivatives that is from here. Okay, then the updated part. this update part is this one. Okay, so you can use this code now to see whether you can estimate the sigma or not. Yeah, let's try to estimate sigma using Newton-Raphson method. So let's following the instruction. So turn off the simulation part so that y variable is the same as in the grid search. So you can compare the result with the grid search. So we turn off the simulation part in the code, right? Then now we have y in the R, so we can just try. Let's try source df. Okay, yeah. Then this is estimated standard deviation, that is 3.59. So we use the 3.6 as true, right? So this is almost very close to true value. And log likelihood is minus 269,973. So let's compare to this value with previously we estimated using the grid search. So we know that the maximum value is around 3.6, right? So that is this one. So can you see? So this is 269,973, and what we estimate from the, so we can copy this one. Yeah, actually they are same, right? Same. So this agree with between Newton-Raphson algorithm and this is from grid search. They are almost identical, right? Yeah, so you can address this question given the practical. Hopefully this makes sense. Then now you can estimate the sigma using grid search or Newton-Raphson algorithm. But what do you think? So which method would you prefer? What is your conclusion about the grid search and Newton-Raphson algorithm? So, in my opinion, Newton-Raphson algorithm is computationally efficient, right? Because grid search need a calculation of likelihood for each point. Then the point is a lot of number of points you should estimate. So, but Newton-Raphson algorithm is within a few iterations you can get the estimation, and their result is almost identical, right? So, Newton algorithm is the preferred method. And now we want to comparing V-based AI algorithm and mixed model equation based algorithm. So uh, I can show the one of Excel file in the teaching material. So this is based on V matrix, how to construct X, Z, A, and V matrix. And this is a mixed model equation. X, Z, A is same, but um, the mixed model equation is different. So when you adding more number of random effects, then this dimension increased. However, in V matrix, whether increasing additional random effects or not, this dimension never changed. That's why this is computational advantage compared to mixed model equation. So if you're interested in more detail, you can have a look at this file. And also, if you can contact me, then we can discuss it further. So let's have a look at the code called airaml.r. And you see the airaml.r. Yeah. And so you need the data file from example 0 dash toy dot phenotypes, and also you need the relationship matrix, and that is stored in this variable. Then that can be used here to read this covariance structure. Then they'll need the starting value for the genetic variance and residual variance, and this goes to construct V matrix, because this is a V matrix based on AI algorithm as shown in the lecture, and construct X matrix. Also you can refer the paper here, and also P matrix, something like this, and log likelihood. And there is AI algorithm follows. So if you're interested in more detail, then you can look into more in detail in this code. But a main purpose of this practical is to actually run this one, right? And before actually running, just simple question. Yeah, what kind of info file needed? That you need the example 0 that can be downloaded from the website that I downloaded already. Then example 0 file should be placed in the same directory as you run the ARM-R, right? So that should be same here. This is the directory, example 0. So this can be downloaded from the web, and you can move into this directory to run the AIREML.R. Did that make clear? Okay, so also you can write model including variance covariance structure written in this code that is in the lecture. So that variance covariance matrix is here, that V matrix, right? So this V matrix is written as here. So you can go through, yeah, so here the V matrix is this one, and the other detail you can also, if you're interested, you can see that this paper, there are more detail of it. Okay, so let's try to run this code in your R. Yeah, then it takes a bit time, more than a few minutes, so I already run it. So if you run, then you can see you get the same output as this, right? So we have around 6 iterations, and it's converged as you can check the last 3 iterations, they are almost same. And the maximum likelihood is minus 487, and the maximum likelihood estimation for residual variance is 0.82, and genetic variance 0.19. So you can work out heritability, right? So heritability is genetic variance, as shown in the first lecture, divided by genetic variance plus residual variance. That's around 20% from this estimation. Okay, so we can go to the lecture 3. Thank you.